corrosion and plating out. Okay, which one of these is oxidation, anyone? This is oxidation, this is reduction. Which one of these happens naturally? Corrosion, yeah, plating out. What kind of cell would that be, generally? Certain type of cell. Electrolytic cell, or the process is called electrolysis. Yes. So these are mostly conceptual. There's only one math question involved in this. What I would turn your attention to is what I have posted, or if you have the practice exam reader, this is what you're going to see on the back of the exam. So let me zoom in just to one little section here. Anytime I don't give you data, you'll need to use this, or if I ask you which will, there's 4 questions I could really ask you. Which will plate out first? Which will corrode first? Which will oxidize first? Which will reduce first? Those are really only 2 questions, not 4, because corrosion is oxidation, plating out is reduction. Those are my very favorite multiple choice warm-up questions that you see at the first 2 questions of an exam. So, for example, if I say which will plate out first, iron or zinc, you would say iron or zinc, which would plate out first? So you need to find them. Okay, so plate out means oxidation or reduction. Reduction, is this oxidation or reduction? Reduction. So the favorable one is what? The more positive or more negative? Positive. More positive. So we're looking on this list for the more positive number, and they're both listed right here, iron and zinc. So we're expecting iron has the more positive number to reduce first or plate out first. In the reverse, we're expecting zinc to oxidize first or corrode first. Does that make sense? So that's why zinc is often plated on iron, or there's galvanized, say, nails or steel, because galvanized means zinc, and zinc will corrode before iron. Okay? So you just literally find it on this list and go from there. There's one one possible type of calculation related to plating out. So let me spend a moment on that. You'll find it in your reader in the electrolysis section. It could be worded in different ways, but typically I ask you for the mass of a metal plated out. And I give you the current. Current is often in what units? Let me get a different color here. Amps, which is a coulomb per second. You'd have to remember that by yourself. So often you'll have the current. You'll be given the time. Time you'd want to put in seconds, so that when you multiply the current and time you get coulombs. So you convert from amps to coulombs via this multiplication. Then there's a constant on the back of the exam to go from coulombs to moles. So you'll find, I'll put this in black, it's basically 1 mole of electron per 96,485 coulombs. So this conversion here drops the coulombs, and now you're at moles of electrons. So because you knew the current, this converts to how many moles of electrons are going through at that same current. All right, then from there, you need a molar ratio. This molar ratio, I'll put this in purple, is the moles of the metal per mole of the electron. For example, Let's say I had aluminum. I'll write it down here, our scratch work down here. Okay. By the way, would this be plating out? Yes or no? The way I wrote the reaction. Yes, because it's a reduction. It's going to the metal. Okay? Going to the ion is corroding, which is the natural process. Okay, so going to the right. So the moles of electrons here would be 1 mole of aluminum for every 3 moles of electrons. Okay, so you need that molar ratio to go right in there. It totally depends on the reaction. It could be 2 moles of electrons per metal, whatever the reaction tells you. And then the last step, because you want mass, is the molar mass. That's from the periodic table. And that's your typical, just like Chem2A, grams per mole. So for aluminum, you're just, oh, there used to be a periodic table here. Okay, it's okay, everybody. It's back. For aluminum, it'll take a little bit to get there, but it's 26.98 grams per mole. So just get that from the table. You do a conversion. Though I could spin the question on you and say, ask for the time, and I give you the mass. So you would just kind of rearrange this. I don't give you this equation because it's just conversions. So you need to be able to convert accordingly to whatever I would ask you in here. Okay? Typical kind of multiple choice sort of question on my exams, if you see those. A very short calculation. All right, let's move on. That's it with those 2 topics. Let me say a short thing about galvanic cells. I already mentioned it. It's just overall in this whole process. So a galvanic cell, the generic term would be a voltaic cell. A galvanic cell is spontaneous. That means E is positive or negative. Positive, yeah, a negative would mean you have an electrolytic cell. That's non-spontaneous, so we're talking about spontaneous here. Though the Nernst equation would work either way. You can use it for any cell you want to. You want to know just generically, you should be able to draw the longhand notation. That is the whole cell diagram, where it looks like it's in kind of 2 beakers or 2 wells. And the shorthand notation. On exams, it's not uncommon to see both, or for me to have you draw one or the other. So just be familiar with generating that sort of diagram. Okay? So that's that for galvanic cells. You'll see me when I talk about these here, I'll mention them even more. Okay, let me say a little bit about batteries.
Question?
Yes?
What were you saying about the positive and negative cells?
Okay, so what you'd want to know about the galvanic cells is that they're spontaneous, so the E or the voltage would be positive. If it's electrolytic, it's negative. Galvanic cells, because they have a positive voltage, are spontaneous. They happen naturally. Electrolytic cells, that's the opposite one. Electrolytic cells have a negative voltage, meaning you have to connect a battery to make that work. That's, as far as conceptually, that would be it. Otherwise, you would need to be able to draw one and find the voltage from the half-cell reactions. So if I told you, hey, this is a battery, let's say I drew a battery for you, you should be able to tell me the voltage by looking on a table like this. Look on a table like this, you find the 2 voltages and you add them together. Okay? Well, when we do Nernst, I'll say a little bit more about that. Okay, let me say a little bit about batteries. A battery is just another type of voltaic cell. I gave you several examples, so you should treat this in the same category as the families of transition metals. So just know what's a primary cell, what's a secondary cell, and what's a flow or fuel cell. And then know the subcategories under that. So for example, there's a dry cell, there's a button battery, there's the NiCad, etc. You don't need to memorize reactions on that, but I would want you to generically know, like NiCad is nickel and cadmium, for example. Yes?
For those kind of questions, would it be like matching?
Those type of questions could either be matching or multiple choice, but you wouldn't really see it elsewhere. If you saw it in a long answer problem, I pretty much am giving you the reactions, so it's cloaked in the terms of batteries, but it might not have anything to do with a battery specifically, besides that it's a battery reaction. Okay? So just light understanding of what the different types are. Okay? For most students, those are pretty easy questions after a quick review of batteries. All right, that's all I have about batteries. Let's get into Nernst and then the K and delta G. Okay? And I'll see if I have an example problem. I'm not sure, but maybe I do. Okay, first of all, let's talk a little review of the equations before we even attempt an example problem. So I'm just going to flip in your reader. It's also in the text as a summary of all the equations. Let me make sure you got these equations down. See if I can get them all on the screen. Okay, so for the top set of equations, that's talking about the standard state. So when you're talking about standard state, that's all the information you have. And you know from the question you're dealing with standard state. So a huge clue in a question is that there's no concentrations given of the different aqueous substances. You're at the top if that's the scenario. If you approach a question and you're given concentrations for each aqueous entity, you're in the bottom scenario. Okay? The bottom scenario is generally you're in a non-equilibrium case, and so you have to use the Nernst or some of these other things. So I got a lot of questions about, well, how do I tell the difference between all those things? What's what? So let's do a quick summary of that before we go on. First of all, so there's some things that somebody asked me that you have to remember from Chem 2B. That's the delta G, the K, and the Q are the most significant. All right, E standard for is positive if it's spontaneous, or I should say just the voltage, or E. Delta G would be negative, and the opposite is true for non-spontaneous. At equilibrium, delta G and E are 0, and K equals Q. So, if you approach a problem, or just conceptually, I guess, know the difference between standard and non-standard. Standard state, that's delta G standard, E standard, and K. Those are a particular value. Do they change as concentration changes? Yes or no? Do these change as concentration changes? No, they don't. They are the same for a given reaction. Other things could change them, but not what we're dealing with, which is primarily concentrations. These, though, change. They can vary widely. Yes?
Can you remind me what K and Q are?
K and Q, K is the equilibrium constant, Q is the reaction quotient. We got that in 2B, all having to do with equilibrium. That's where you take the concentration, say, of the products divided by concentration of the reactants. You need both of them in Nernst and Nernst-related equations. Typical for me to ask you to calculate one of those on an exam. Okay, whether delta G, K, or Q, or something within them. So within Q is concentrations, typical calculation. All right. So let me flip through one of my binders here, see if I can find an example. If not, I will wait. We can wait for the, oh, hey, what's this? Looks like good stuff. Here's a good one. Here's a good one. Oh my God, that's good stuff. Let's see, I guess this one looks different-ish. Okay. So, standard state problem or non-standard state problem? What do you think?
Standard.
It's a standard state.
Yeah, 'cause there's no concentration.
The big giveaway, again, no concentrations given. Okay, if there's no concentrations given, then you're going towards standard state. Let's try to solve this, and I'll give you an example of a non-standard state for the same one, okay? So let's work on this. This is a very typical sort of question.
down a little bit? Thank you.
Everything okay? Okay. So for this one, I give you in shorthand form this. So I don't give you the reactions. You gotta figure that out all by yourself. So for example, we know the first one is the anode or oxidation or reduction. Oxidation here, we know this is reduction. So you have to know that. The oxidation is listed first. So I can either at this point, whatever is easier for you, you can either balance this reaction in oxidation, or if you're freaking out, you can find it on here. It could likely be here. Okay? Same is true for the copper side. You can either balance this or find it on here. Now, on the exam, if I don't give you the reaction or the voltage, that means it's back here. On homework, I don't care, right? So I give you whatever, whether it's here or not, because you can find everything on Google. Okay? So you see the difference? So you might approach some questions from the past, say homework or what you've seen a lecture. It's not on this table here. That's totally normal. On the exam, I have to give you stuff on the table, or I have to give you the reaction and the voltage. Okay? So I can't have you memorizing stuff. So if you ever are not sure about reaction, on an exam it has to be on the table because you're just limited to that information. Okay, so let's just write these reactions from scratch though. So, an oxidation, chromium goes to chromium 3 plus 3 electrons. Well, let's just double check. Is that an oxidation? Yeah, I've written it as oxidation, so we're good. Copper 2 plus 2 electrons goes to copper solid. That's a reduction, correct? Okay, so we're good with oxidation reduction. It matches that. And also notice nicely, the order of writing the oxidation or reduction kind of follows the order that it's written in the battery. That's true for simple batteries. If the battery gets more complicated, you do need to think a little bit more about writing these. But generally, it kind of follows this order. Chromium before the chromium 3 plus, etc.
Question?
Okay, so there's the reactions. Let's get the overall reaction because part A said, write the overall reaction. I'm going to multiply this by 2 and this by 3 because I want the least common multiple of the electrons. Those must cancel. They're the intermediate of the reaction.
Question?
So, 2 chromium plus 3 copper 2 plus goes to 2 chromium 3 plus. Oh, yeah. Go for it. I don't see you. But...
Hello.
Oh, hi, way up there.
So, on the state symbols, how specific do we have to be with those on the test? Do we need to write them? Can we just like pretty much ignore them? Or?
What do you do with the state symbols? Usually in the batteries or galvanic cells, voltaic cells, I want the state symbols, and I typically will write in the question, include state symbols.
Okay.
The place that I told you in class that you don't have to worry about state symbols is the reactions that you're seeing in the transition elements section of the transition metals. Mostly because they're often industrial, so without knowing the conditions, you basically have to memorize the state symbols. However, these reactions often happen under standard condition.
Right.
So based on what you've already learned in 2A and 2B, you should be able to predict the state symbols. So for example, for part A was a typical question, I want the state symbols here. Now you might be wondering, how would I know that? Well, for a lot of these, electrochem reactions are not too bad. If you see an ion, it's aqueous. So I see ions here, it's aqueous. I didn't finish the reaction here, copper. If you see a lone element, that is a metal, it's a solid. Just like any metal you've ever seen except for, say, mercury. Done. The other way you could have done it is I wrote the states up here. Okay? So, but I would expect you to be able to generate these states had I not written it up there. Okay? Again, if it's an ion, it's aqueous. If it's a lone element, solid. And that'll get you through pretty much everything. Okay, so it's that easy.
All right, thank you.
Yeah. Okay, that's part A. There's the reaction. We want the state symbols. It looks all balanced. We're good. Part B. So that's A. Part B, what's N? 6, it's the number of electrons that cancel. Part C, so B was easy. C, okay, delta E equals minus N, delta E standard minus E squared. Okay, if, just make sure you see it. This has a state symbol here. The state symbol goes with the state symbol. There's no state symbol here to get, if there's no state symbol here, there would be no state symbol there. And then in that case, how would I find this variable when it doesn't have the state symbol? I need one equation. Nernst. If it has the state symbol, in this case it was given to me, right there. But if it wasn't given, how do I find the E with the state symbol? From tables. Yeah, from the reduction potential table here. State symbol, you get it from the table. If the E does not have a state symbol, you get it from the Nernst equation. We'll talk about Nernst in just a second. Okay. So this would just merely be minus 6 moles of electrons. F is 96,485 coulombs per mole of electron. And then it was given in the question 1.08 volts. A volt can be simplified to what other units? Joules per what? Coulomb. Yeah, so the coulombs will cancel, and that's how you get joules as the answer in delta G. Is this cell spontaneous? Yes or no? Yes, because E is positive. So it happens under standard state, so you just look at the E standard. If it was not a standard state, you look at the E without the standard. Okay, let's talk about the Nernst equation now. Let's say, so this was not part of this question as I wrote it, but let's talk about Nernst for a moment. Let me move this out of the way. Oh, the answer, was there an answer? In my mind there was an answer, but I can't find it. So I'm sure it's hopefully not hard to calculate. Okay. So let's look at the Nernst for a second. Yeah. This answer would be in joules, that's right. What I wanted in, you have to read the question. If I don't specify, you can put in kilojoules or joules. If I do specify, just go to whatever I ask for. Kilojoules is a pretty common unit, so in that case you'd have to do what? Divide by 1,000. Yeah, it is straight there. Okay, here's the Nernst equation. If I ask for E without the standard, you need to use this. So let's look at the pieces here. Make sure we got that. This is a given value, 1.08. Again, it's given in this question. If it was not given, you get it from the reduction table on the back of the exam. N is again what? 6. Okay, let's look at Q. Because this is a little blast from the past from Chem 2B. Make sure we got that. If I'm using Nernst, I must have the overall reaction. Okay? If I'm not using Nernst, I actually don't need that overall reaction. I only did it because the question asked me. However, for part B and C, I did not need the overall reaction. But if I'm going to do Nernst, I must have it because I need it to write Q. So let's write Q. Ignore solids, so I'll just cross it off on this part. Ignore the solids and ignore liquids. Then you go products over reactants. So the question earlier about what's Q or K, here we go. For either of them, you'd write products, so you include aqueous or gases. Whatever's present. So chromium 3 plus is in the products. There's 2 of them, so I raise it to that exponent, squared. And then in the denominator, which is the reactants, there's a copper 2 plus. That is cubed. So you raise the power to the exponent. In the kinetics chapter, we have not derived where this came from. When we get to kinetics, which is the upcoming unit, we'll actually derive where this equation comes from. Yes?
So you don't include solids?
You do not include solids nor liquids. Only gases or aqueous.
For K, do you include solids and liquids?
Neither for K nor Q do you include solids or liquids. Only gases and aqueous. K and Q are the same in that way. Okay. All right. So if I gave you, let's say if I said, oh, there's chromium 3 plus at 1.0 molar, and there's copper 2 plus at 2.0 molar, I'm telling you, hey Folios, use the Nernst equation and plug these numbers in here. And then probably you're going to be asked for E. The other very common variant of this is I give you the cell voltage, okay, and then I give you one of the concentrations and I want you to find the other. So for most people, the problem is not setting it up. The problem is the math. So make sure, if you feel, even if you feel comfortable with logarithms, go back to one of the examples from lecture or look in the practice exams and actually do the math. Because that's a common place to make mistakes. So you'd rather have the people who are not here make that mistake and you all do it right. Okay? Okay, that's Nernst K and delta G. Any other questions about that? I'm sure there'll be some example specific questions later. No? Okay. If none, let's go back to the flow chart or what I was working on over here earlier. That's all of electrochem. Let me say one thing about electrochem before moving on. Electrochem, if you had to guess what the big long answer question is, you would guess Nernst or related equations. Okay? So everything else could be a short calculation or paired onto a long answer or in matching or what have you. Make sense? So make sure you do some of those kind of like longer calculations. You'll see them pretty much in every exam, so they're not hard to find. Okay.